Section 7.3 is entitled Using the Central Limit Theorem. And basically what this section covers is just recognizing when to use the central limit theorem and when to use just the distribution associated with the data. So I'm not sure that this section really deserves, I'm not sure this information deserves its own section in the book. It could have been lumped in with sections 1 and 2, but this is the way the author decided to do it. So basically, the key is if you're being asked about the probability of a particular mean value, then we use the central limit theorem for means. If we're being asked to find the probability of a particular sum for a sample, then we use the central limit theorem for sums. But if we're being asked to find the probability for individual values, then we don't want to use the central limit theorem at all. Okay, we just want to use the distribution that random variable follows. So for us, because we're doing continuous distributions and we've only done 3, it'll either be uniform, exponential, or normal. So remember that with the central limit theorem, as we take larger samples, the sample means tend to get closer to the true population mean, and also as n gets larger, the standard error gets smaller. So remember that the standard error formula is the standard deviation divided by the square root of the sample size. So because you're dividing by the sample size, or the square root of it, the larger the sample size gets, the smaller that fraction gets. So the standard error goes down as we take larger samples. This first example will be about the uniform distribution. So we see here we have a study concerning stress among college students, and stress scores were given a uniform distribution with the lowest score being 1 and the highest being 5. So that gives us a mean of 3 and a standard deviation of 1.15. So with a sample of 75 students, the first thing we want to find is the probability that the mean stress score is less than 2. Okay, so describing this in terms of the notation, we're trying to find the probability that x bar is less than 2. So because we're dealing with the mean, this is a central limit theorem question. So the central limit theorem formula for means says that we take 2 minus the mean, which was 3, divided by the standard error, which is 1.15 divided by the square root of our sample size. And that gives us a z-score of negative 7.53. Okay, this is a very, very negative z-score. And if you refer to the table that I linked in chapter 6, you'll notice that there is no row for negative 7. Okay, the lowest it goes is, I think, negative 3 or 4. Might be negative 3. So, and you'll notice that those scores are, the probabilities or the areas to the left of those scores are basically 0. So to be at negative 7, it's even smaller than that. So instead of trying to write out a whole bunch of decimal places with a bunch of zeros, the way that we're going to express this answer is just as 0 plus. Okay, it's a fairly common notation when we're talking about a very small value, very close to 0, but not quite 0. Okay, so the probability that x bar is less than 2 is very, very low. Okay, it's not exactly 0, it's not impossible, but it's very, 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 very low. Part B of this example asks us to find the 90th percentile for the mean stress score. So here we have the 90th percentile, P90. And so what this means is we need to go to the table and figure out what's our z-score that is as close to an area to the left of 0.9 as we can get. Okay, we're trying to get 0.9 to the left of our z-score. So looking at the table, I didn't copy and paste the table in on these examples, but I found 1.28 to be as close as I could get to 0.90 on the area. So I take 1.28 as our z-score, set it equal to the central limit theorem formula, and we're going to solve for x bar. So doing the math for you here, just multiplying by the standard error and adding 3, we get x bar is 3.17. So this is the 90th percentile for the mean of the samples. Part C asks us to find the probability that the total stress score is less than 200. So this is where you kind of have to use your, your smarts, your savvy, and understand that what they're asking for is a sum. Okay, when it says total, typically total means that we've added to something altogether, right? Like a sum. So this one's asking us about the sum, so we're going to use the central limit theorem for sums on part C. So here we have sigma x less than 200. So our formula for means is going to be this 200 value minus the sample size times the mean, so 75 times 3, divided by, and remember in the sum formula, the standard deviation 1.15 gets multiplied by the square root of the sample size instead of divided. So this gives us a z-score of negative 2.51. So this one is pretty easy to find in the table. So right here at 0.00604, and that's our answer. Since this is a less than question, then the area to the left is what we need, and so this answer is the correct answer. Our second example is an exponential distribution example. This one has to do with cell phone companies and contracts and customers going over their minutes on their phones. And supposedly, according to this, the excess minutes, okay, so for the number of minutes that people go over their plan allotment, follows an exponential distribution with a mean of 22 minutes and a sample size here of 80 is what we're going to consider. Now notice that you're not given the standard deviation on this, so there's a reason for that. And that's because we learned in Chapter 5 that the exponential distribution has a standard deviation that is the same as the mean. Okay, so the mean is 22 minutes. The standard deviation is also 22 minutes. So you may not remember that little detail from Chapter 5, but we're going to need it for this example. Part A asks us, find the probability that the mean excess time is longer than 20 minutes. So here we have x bar greater than 20. Is the probability we seek. So we set up our z-score formula with the central limit theorem for means, and we get a z-score of negative 0.81. So in our table, that would be right here at 0.20897. So this is a greater than question, so we can't leave it as this. We have to subtract 1 minus that value, and it gives us an answer of 0.79103 for the probability. So the probability that the mean minutes that these people go over for a sample of 80 people, the probability that that would be greater than 20 is 0.79. For part B, this time we're just going to consider one customer. Suppose one customer is randomly selected. Find the probability that this person's time is longer than 20 minutes. So because this is not a central limit theorem question, we have to refer back to the type of distribution that this data follows. So this was exponential, right? So if I want to find a probability involving an exponential distribution, I have to use the exponential CDF formula. Okay, remember that was one of the few formulas that you had to know going into the midterm. That was one of the few things you had to memorize. So the formula is 1 minus e to the negative mx, where m is 1 over the mean. So here we have 1 minus e to the negative 1 over 22 times 20. 20 is our x value, and that gives us a score of a probability of 0.5971. But remember that the CDF formula always gives you the area to the left. So in order to find the solution here for x is greater than 20, we need to subtract 1 minus that value. So we get a probability of 0.4029. Now part C of this example, I did not show you on the slide itself, but it prompts you to answer the question, why are these two numbers different? Why for the means do we get 0.79 and for individuals we get 0.40? Well, I would ask you to ponder that question and see if you can come up with a reasonable answer on your own, and then perhaps this could be something that we discuss in our next office hours or on Perusall. However you guys would like to interact is totally fine with me. But it bears some consideration. I think it's worth thinking about. Why are these answers different? And what should we expect in terms of which one should have a higher probability, which one should have a lower probability. For your homework, you've got a few problems here out of the practice section, 37 through 60. That should give you enough practice determining when you're using central limit theorem, when you're using some other distribution, and let me know if you have any questions. Thank you very much.